So welcome to lecture 7. So we'll continue our journey through random variable. Hopefully by today we'll finish this part, random variable, and we'll continue with random process in the next class. So today is 28th. So the first topic we'll take today is random, like function of random variable. So many a times, suppose, and we are starting with say one random variable. So suppose you have a random variable x. So just think about the geometry. What is x? X is basically a map from the probability space to the real line. So you can visualize it, right? So this is suppose the sample space, and from here, actually it is the Borel, the sigma algebra. From sigma algebra the map is provided, but we can visualize that element of sigma algebra is essentially some subset of this sample space which is mapped to the real line. So the Borel sigma algebra of the real line is basically the sigma algebra which is generated by the intervals of the form of -infinity to x. That is required for generating the distribution function. So your random variable is essentially a map of this sort. Now I am generating some, and random variable means real valued random variable. So random variable is used for real valued thing which is mapped to real line. So if it is complex valued, we will say that to be a complex random variable. Okay. So when I am saying a function of a random variable, essentially it is a map from this real line to another real line. So there is some other real line, it is mapped from here to there. So suppose let us start with one example that will be easier. So I'm basically talking about some function y is equal to some function, say g of x, where x is a random variable. So x takes values on this real line, I am mapping it to another real line. This is a real valued function. Okay. So let us start with a couple of so what we can see that this may be y which is equal to g of x. However, the entire thing, so finally you are taking values in this real line, and the original point is the probability space. So this is also a random variable, right? So this is the composite function, you can say. So this is g of x. So x itself is a function, so this is composite function g composite x. We can visualize it like this. So let us take some example, and since this is a composite function, this is itself is a random variable, there should be some distribution function developed on this as well. So what will be the distribution of this new random variable y? Because that is not obvious. For x, this random variable, the distribution is suppose known. So the induced measure, which induced probability which you are getting is f. So f is the distribution of x, distribution function of x. So can we get the distribution function of y for all functions? We don't know, but let us see. Let us see with some simple examples. So let us take the linear function to begin with. So y is equal to say ax plus b, and I am taking for a positive. So if I think about it, like if I plot x and y, suppose the values the random variable x takes and the random variable y takes values small y, then this is a linear equation, and it is like this, where the intercept is b. B can be positive, negative, anything, bias, but I am restricting that this is having positive slope. So this slope is tan theta is a. Okay. So what kind of distribution this new random variable y will generate? Let us try. So suppose the distribution function, okay, for x I am writing it to be capital F subscript x, that is the distribution function of x. Here I am naming it to be capital Fy to be the distribution of y. So what will be capital Fy of some value y? That y can be any value on this real line. So essentially these two real lines we are juxtaposing like a x axis and y axis, okay, to relate the random variable on x axis to the random variable on y axis, and this relationship is a straight line which is ax plus b. So this probability, this distribution function is essentially the probability of this random variable y is less than equal to y. That is the probability. Now I know that capital Y is basically x plus b. So probability of ax plus b less than equal to the value y. When I am writing in small, it means the value. When I am writing in capital, it means the random variable. Okay. So now I can do that trick. So ax is less than equal to y minus b. And since a is positive, so this is equal to probability a x is less than equal to y minus b by a. If a is negative, then we would have to reverse the inequality sign. So that's why I have taken this to be positive. If it is negative, you could have done it, but you have to reverse the sign. So what is this? This is essentially, now you are talking about probability of the random variable of x. So this entire thing is nothing but the distribution function of x. But what is the argument now? The argument is y minus b by a. So you see, so whatever be the distribution function given, from there you can generate the distribution function of y by this transformation. So what is the density? If the random variable is continuous, then you can compute the density as well. So if x and y are continuous, then we know that density function is essentially the derivative, which is equal to d fx y minus b by a dy, which is capital Fx y minus b by a into 1 by a. So by this function you can connect the density function of y, the PDF probability density function of y, and this is the probability density function of a. Okay. I can take some other a little bit of complex functions. Say let us take the parabolic function, say quadratic function. Okay. So for a quadratic function, say y is equal to ax square plus b. Again I am taking a to be positive. If negative, you have to do in a different way. So now in the same way I will compute for the distribution function. So distribution function of small, the for y is nothing but probability of y is less than equal to small y. Now what is y? Y is ax square plus b. Less than equal to y. What is that? Since a is positive, so x square is less than equal to y minus b by a. Now this is interesting because now this is equal to probability modulus of x is less than equal to y minus b by a square root. So that probability is essentially probability of x lies between y minus b by a and greater than equal to minus y minus root over of y minus b by a. So this is the probability what is the distribution function of y. Now what is this? This I can write as probability of, so this is the higher term, the positive term, this is the negative term. So this I can write as probability of x less than equal to root over of y minus b by a minus probability of x less than equal to minus root over of y minus b by a. This is obvious, right? So if I draw the line, suppose this is minus root over of y minus b by a, and this is say plus root over of y minus b by a. So this probability is nothing but of whatever probability is there in between this area. So this area can be written as the entire area from minus infinity to this point minus the area from here to here. So suppose this is the density function curve. So I can write that the area under this is equal to area under the entire thing, which is this, minus area under this. right? So what is this? This is the distribution function of y minus b by a minus this is the distribution function of minus y minus b by a. So this is how I can get the distribution function. Find out the density function. Density function if x and y are continuous. Okay. So this density function, if you compute, just quickly check that it will come down to be f y y will be equal to the suppose these are the two roots. I am naming them to be, this is x1 and this is x2. Then it will be fx x1 divided by modulus of g dash x1 plus fx x2 divided by modulus of g dash x2, where g is basically the derivative of gx is basically this function, x square plus b. So gx is basically x square plus b. So g dash is equal to 2ax. Yeah. So basically you are doing for y is equal to gx. For this random variable you are working on, and I am writing on in terms of the real argument, small x, which is the value. So it is ax square plus b. So g dash is 2ax. So you just put these values, and this x1 and x2 are the roots. So this result can be generalized for any number of any function g which is having the corresponding roots. So I can I'm without proof, I am just stating the result that for any random variable so for any random variable y is equal to, say this is the third result, y is equal to gx, and assume that roots are roots of gx is equal to y are x1, x2 to say xn. There can be n roots for any n. Then the density function. So if this is both are continuous random variable, x and y are continuous, and this is for any particular y. Okay. So when y changes, the roots changes, of course. So then the density function of y will be summation the density function of xk divided by modulus of g dash xk. This is for k is equal to 1 to n. So this will be the computation of density function for a general case. Now after this, where I am planning to go, we are talking about one random variable till now. So this is something when there is only one random variable, even if we are talking about functions of random variable. But then we can think of that what will happen if there are two random variables. So suppose there is x and there is y. It is possible. It is possible to encounter multiple random variables, or even when we are talking about say complex random variable or random vector, it is possible that every element in that random vector they are independent. So it can be a like n tuple, so n random variables simultaneously. So we have to understand that how two random variables interact with each other. So before going there, so the next topic is basically like two random variables. So before going there, I would like to bring some memories from the concepts of probability. And in probability, basically when there are multiple sets, not just one set, Then the concepts of joint distribution, conditional distribution, or joint probability, conditional probability, marginal probability, those things are required. Those we will like take first before going into the random variables, so multiple random variables. Okay. So we can start with suppose there is a probability space. So probability space is this one, and in that probability space suppose there are two sets A and B. So what we know from our elementary set theory understanding is that the probability of A union B is probability of A plus probability of B minus probability of A intersection B. This kind of result is there in Boolean algebra as well, right? So what rule is this? This is naive set theory rule. You should know. This can be quickly checked using elementary set theory application. Suppose this is A, this is B, then you know that the entire area is union B, and this area is A intersection B. So from there this particular formula is written straight away. But I want to see something else. Okay, this result will be useful in information theory as well. So right now I am just mentioning, but we will come back while we will discuss about information. So from this kind of construction, when there are two sets, now we don't know whether they are overlapping or not. So overlapping, if they are not overlapping, if their intersection is null set, then we know that the probability of the null set is 0. Then the probability is additive, right? Otherwise we say that probability is sub-additive. Sub-additive means what? Sub-additive means probability of A union B is less than probability of A plus probability of B. So that is called the sub-additive property of probability. We discussed about this in the very first class. So sub-additive property is basically probability of union of some sets I is equal to 1 to n. This is always less than equal to summation of probability of I is equal to 1 to n. So that is obvious from this. Now if the intersection is null, if they are disjoint, if AB are disjoint, then we know that this is additive, PA plus PB. Now we want to go to something called conditional thing. So conditioning events. So we'll talk about conditional probability a little bit more. So suppose you have these two sets A and B, and you know the occurrence of a particular set, suppose B. So if you know the occurrence of a particular set B, then what probability is there lies in that set A, provided you know about B. So that is called the conditional probability of A given B. So probability of A given B when B is known, B has already occurred. So now what is the probability of A? So that is basically from this diagram you can visualize this, that suppose this is the uncertainty, this is the probability of A, this area. Now if B already occurred, then this thing is known, this amount of information is known. So what probability is left, that is the probability which you are left with, that is called the conditional probability. So there is a way of computing this, and this is the famous chain rule by which it has been done. So this is basically the joint probability of A and B, which is basically A intersection B divided by the probability of B. So within B, at what what is the percentage of overlap of A intersection B? What is the percentage of overlap of A in B? That is the probability of A intersection B, and that the ratio of that in PB, that gives you the conditional probability. There are some really good derivation of this conditional probability proof, but it requires naive set theory. Again, I am assuming this to be a prerequisite. You know this result from your school days, so that's why I am not deriving them again and again. I am just mentioning them because this will be required. Okay. So there are some nice rules for conditional probability, for example Bayes theorem, but I am now skipping it. Bayes theorem will come back again while working on detection theory and estimation theory, the so-called maximum likelihood and maximum posteriori estimation and detection. we will invoke it there. So right now I am just leaving this, but chain rule you can see from here that iteratively or recursively calling this formula, you can compute intersection of any number of events. Suppose I is equal to 1 to n, and you can write it as product of probability of say a1 into probability of a2 given a1 into probability of a3 given a1 a2 into probability of an given a1 to an minus 1. So I can write it as product of k is equal to 1 to n probability of ak given a1 to ak minus 1. So in the first case, when k is equal to 1, so there is null, actually there is nothing. So a1 given a1 is basically a1 itself. Sorry, a1 given a0, there is no a0, so that is basically the null set. So given null, so it will be pu a1 itself. So this is called the chain rule. By the conditional probabilities you can compute it. Now you can clearly see that if two events, we say two events are independent if the knowledge of B does not give any information about A. So this probability is just PA. So from here we can talk about independence as well. So independence is what? Independence is when knowledge of one set B, knowing B does not give you any information about A, does not increase any probability of A. Probability of A. Then probability of B intersects B given A, or sorry, probability of A given B is nothing but probability of A, whatever is there. So what does that mean? That means that probability of A intersection B by PB, that is the conditional probability, will be equal to PA. So that gives us the familiar expression that for two events A and B, probability of A intersection B is nothing but probability of A and probability of B. Okay. So these results are required, and from here we can go towards again like when we are coming across two random variables. So when there are two random variables, so suppose there is one random variable x and another random variable y, both are defined in the same space to the same real line. Okay, but for the sake of simplicity, for the sake of convenience, I will draw visually in two real lines. So basically this will make them, when I'm taking them jointly, both x and y simultaneously, then I can visualize them in R2, in two-dimensional space. So this is basically a two-dimensional space R2. So this is one real line, this is another real line, and this entire R2 space is the Cartesian product of those two real lines. And this is your probability space, suppose. So your x, suppose I am mapping from here to here, and y I am mapping from here to here. So this is your so-called x-axis, this is your y-axis. Y takes value here, x takes value there. And you have your like distribution function separately. Now what we can like think of in this mapping, that suppose since we are making these two random variables in a R2 space, in a two-dimensional Euclidean space, where x-axis is the first random variable x and capital, and y-axis is the second random variable capital Y, then we can visualize that these two random variables are nothing but a joint random variable in that R2 space. Okay, so from here you can see that how two-dimensional random vector is obtained. So basically two random variables is nothing but, you can visualize that to be a random vector as well, right? X and y, these are the two random variables which you can write like a vector, so it becomes essentially a vector. So this distribution which you are obtaining, you can visualize that, okay, I want the joint distribution of the both the random variables. So what do you mean by joint distribution? So joint distribution I can write down as fxy of two numbers, say x and y. So this is the joint distribution. So it basically says that what will be the probability that x will be less than x and y will be less than y. This probability. So if you really want to think about the sigma algebra generated by the R2 space, basically you have to think of that how what is the geometric structure of these two inequalities. That is basically the semi-infinite rectangular shape or square shape, whatever you want to say. So suppose this is the x comma y coordinate and this area. So minus infinity to x and minus infinity to y. This entire area starting from minus infinity this side and minus infinity this side. So whatever probability is there in this entire region, that probability is essentially the joint distribution, and this is called the joint distribution of these two random variables. Now I don't know how these two random variables are related. They may be independent, they may not be independent. So this joint distribution directly I don't know that how to split them in terms of their independent, their separate distribution functions. So x and y, they have separate distribution functions, right? So those will be named as marginals. Now how to get those marginals if this is given to you? Okay. So what do you know about marginals? Marginals, we know that fxx is nothing but the probability of x less than x, and marginal of y, which are the distribution function of the single random variables. So over the two real lines. So I give them new name to be the marginal probability distribution of the two random variables x and y. So what we can, how we can compute these from this? Let us see that. So capital Fxx is nothing but probability of x less than equal to y. Now x less than equal to x. So now we can think of that this is equal to like I can integrate this in this way, that probability of x less than equal to x, and let us check what is the probability of y is less than equal to some value y. Then I will integrate this probability over the entire y. So this is over the entire real line y. I can write this to be ry or something. That is understandable. So this is basically running from minus infinity to infinity. So whatever value y checks, I compute this joint probability and that I integrate over the entire real line for y. So that will give me my marginal. And this I can write down. This is essentially the density function. Actually, I should not write this dy here. I actually integrate over the probability in true sense, because when I am writing about the probability is basically of the entire set. So I am integrating over this. And this is basically the y-axis which I am talking about. So this is basically the integration over the joint distribution function. So over the R, and I am talking about this xy, and I am doing it over y. So the integration of the joint distribution function over y-axis gives us basically the marginal of the x-axis. Similarly, integration over the x-axis will give you the marginal of the random variable y. Okay, this thing will be like easier to represent or easier to compute when they are, say, continuous random variable. Then this like Stieltjes differential, it can be written as the density function small f xy dx dy, etc. Right. Nevertheless, I am not writing that right now because I hope you can understand this. Okay. And now when you have two random variables, so like similarly, just like we have done for single random variable, we computed different kind of moments, for example the first moment, second moment, etc. So we can do this here also. So when you have two random variables, what we can compute? We can compute the corresponding moments. So the moment problems. So here the basic moment, there is no one moment because we already have two random variables. So when you consider both of them, so it will be a second moment obviously. So the corresponding moment is called correlation. This is another definition. So correlation is basically the moment of both the random variables, the product of them. So here we are talking about real, so it is just x and y. So this we can compute as over the entire plane, we compute by dfxy. Okay, so here this is the joint distribution function. If this is continuous, if x and y are continuous, then we can write this as R2 xy f. I can write it to be xy to mark that these are essentially the joint dx dy. We can write like this. Or if they are discrete, then I can write in terms of the mass function. I can work on this mass function. So x k y j or something like that. I can write two sums. So p m x k y j, or p is the probability mass function, and here I can write that k runs from say two indexes. So suppose capital X takes values in x1 to xm, and capital Y takes values in yn, suppose. So this is equal to 1 to n. So for discrete, this is the formula. For continuous, this is the formula. Okay. This correlation will be another extremely useful tool for understanding multiple random variables, and we will go in detail while using them in different points in our particular course. The second moment which we can relate from here, so it is like the regular second moment, but we can always compute the central moment, so which is named to be the covariance. Just like the variance, we name this to be covariance. So covariance is when for both the random variables x and y, we centered it around its mean. So this will be basically the expectation of x minus ex. These means are essentially computed using the marginals, as you understand, y minus ey. Okay, so that you can compute in the same way. So actually we can do more tricks. In the last class, in the variance class, I should have already discussed it, but nevertheless let me do it first here, then I can show that what will happen for the variance case. So I can, since this expectation is a linear operation, this is a integration process, so this expectation is nothing but integration, so this is linear very much, or sum, that is also linear. So I can multiply these two factors and I can write it as xy minus ex into y minus x into ey plus ex into ey. Now this ex into ey or ex ey, they are basically real numbers, they are constants. So I can take xy inside because expectation is a linear operation. So if I take that inside, so it will become expectation of xy minus expectation x into y. Now expectation of x is constant, that will come out of the outer expectation. Okay, so it will become expectation of x. Now you are doing expectation over only y. Now this expectation is joint expectation over both x and y, but when you are running it over only y, so the probability distribution function or probability density function or whatever is there for x, that will give you only 1. So you will get it only expectation of y. I'm like doing a little bit of step jumping because this expectation I did not explicitly write over which you are taking the integration. Nevertheless, you can understand. So this is again, this expectation of y goes out, and this expectation goes in only to x. So you will get expectation of x into expectation of y in the same way. Plus finally, this is a constant. So if you take them outside, what remains is basically unity. So now you can see clearly that these two will cancel out. So you will have this simple formula, expectation of xy minus expectation x into expectation y. So this is the covariance formula. Okay. So you can relate covariance with correlation. So this is correlation minus the means of x and y. For variance also we can have a simpler representation like this. So what is variance? Variance is x minus expectation of x whole square. So that is variance of x, right? Sigma square of x. So this I can write in the same way. So x square minus 2x expectation of x plus expectation of x square. So this is equal to expectation of x square minus 2 expectation of x, that goes out, this expectation go in, and that works on x. So expectation of x again plus expectation of x square. This is minus 2 expectation x square. So this will be equal to expectation of x square minus expectation of x square. So I get the similar kind of expression for correlation and covariance and variance, when covariance for two random variables x and y, and variance for just x. Okay. So yeah, these are fine. But now I can have some other kind of questions. For example, for these two random variables, if I design some functions of random variables of these two random variables, what will happen? For example, let us take the simplest one first, because this is of like interesting like usefulness. Suppose I work with the simplest scenario when x and y are independent. So okay, what will happen when x and y are independent? So if x and y are independent, then we know that the probability, the corresponding probability of occurrence, these like density function, for example, fxy, that will become the marginal. So the joint probability density function will become the product of the marginal probability distribution function, density function. So this I am like stating with even without proof. So when the probability, the random variables x and y are continuous. For discrete also we can have a similar expression where I write, I can quickly write it. So pxy for say xk yj, that will be equal to px for xk into py for yj, and this is true for all k and j. Okay, this is also true for all x and y. X and y are real numbers. Okay. So from this condition you can easily show that if they are independent, then the expectation is also the correlation, what I have written, that will be equal to the product of these two, such that the covariance will be 0. So for independent, the covariance will be 0. And we say that they are uncorrelated. We will say that they are uncorrelated. So this is obviously like the forward way of saying that if two random variables are independent, they are uncorrelated. However, the reverse is not true. It is possible to have two random variables uncorrelated. However, they are not independent. That is possible. We may take one example later on. Okay, to have x, y uncorrelated but not independent. Independence is actually a deeper result, topological result we can say, which works in the probability space. Uncorrelation or uncorrelatedness is essentially not only depend on the probability but also depends on the values the random variable takes. So it depends on the assignment as well, not only on the probability. It definitely depends on the distribution. Now if x and y are independent, then I want to have this particular result. I want to see that what is the distribution function for say z is equal to x plus y. This is important. So what is the, when x follows say capital Fx, this is the distribution function. Y follows capital Fy. Then what is say Fz in terms of those two distribution functions known, Fx and Fy. So right now I wrote as distribution function, but I will show you separately for discrete random variable and continuous random variable. Mixed I am leaving it. Okay, so if you take discrete random variable, I'll show you one quick example. So discrete random variable, suppose x takes values, these following values, say 0, 1, 2 and 3, okay, with probabilities say p0, p1, p2 and p3. So these are the corresponding probabilities. This is the probability mass function. So p0 plus p1 plus p2 plus p3 is equal to 1, obviously. And suppose y takes some values, say 0 and 1, suppose, and their probabilities are say q1 and q2. So q1 plus q2 is equal to 1. So if you ask me that, I can take negative values also, say, yeah, it will be nicer if I take negative values as well. So this is a q3. So q1 plus q2 plus q3 is equal to 1. Okay. So it takes 3 values, it takes 4 values. Now if I know that they are independent. So what does that mean, they are independent? They are independent means the joint probability of occurrence of x and occurrence of y, they are independent. So I can generate the joint distribution function of x and y quickly. So I can make a table, okay, if they are independent. So suppose x takes values this side 0, 1, 2, 3 and y takes values this side -1, 0 and 1. So the joint occurrence of x 0 and y -1 will be the product of the marginal. So it will be p0 q3. So it will be p0 q3. This will be p1 q3. This will be p2 q3. This will be p3 q3. Isn't it? This will be p0 q1. This will be p1 q1. This will be p2 q1. This will be p2 q2. P3 q1. This will be p0 q2, p1 q2, p2 q2 and p3 q2. So if this is independent, it is pretty obvious that the marginals will be sum of these joint probabilities. So you can compute the sum over x to get the marginal of y. So I can quickly check that p y is equal to -1 will be equal to sum of p y is equal to -1 and x is equal to xi for I is equal to say 0 to 3. So these are same. So it is same as saying that probability of x is equal to 0, y is equal to -1 plus probability of x is equal to 1, y is equal to -1 plus probability of x is equal to 2, y is equal to -1 plus probability of x is equal to 3, y is equal to minus 1, okay, which is equal to P0 Q3 plus P1 Q3 plus P2 Q3 plus P3 Q3. So you can take Q3 as common. What is left is P0 plus P1 plus P2 plus P3, and that sum is 1. So you get the Q3. That is your expected marginal value of the probability mass function, isn't it? So that's fine. So you understand that how marginal and joint works. Now I ask you the question that what will happen if you take the random variable z is equal to x plus y. So clearly x can take values from 0 to 3, y can take values from minus 1 to 1. So what can z take? So z can take value like minus 1, 0, plus 1, plus 2, 0, 1, 2, 3, 1, 2, 3, 4. So it can take minimum value of minus 1 and maximum value of 4. But at what probability? So it can take all the values, minus 1, 0, 1, 2, 3, 4. These values it can take. But at what probability? If we know the distribution functions of x and y, the probability values to be P0, P1, P2, P3 and Q1, Q2, Q3, then at what probabilities these value will be taken? That is interesting to see. So let us write like this. So probability of z is equal to, let us take one example. Say what value it will take for 2. So how to compute? So z is equal to 2 means probability of x plus y is equal to 2. Now x plus y equal to 2 can happen in different ways. So what ways it can happen? So I have the chart ready. I am writing it again to check quickly. So x takes values here, y takes values here, minus 0, 1, 0, 1. So where x plus y can be 2? So it can be x is equal to 0. No, it will not happen. But x is equal to 1, y is equal to 2. That will happen. So it will happen here. So if I draw a grid where it is happening x plus y is equal to 2, out of these 12 elements, there are total 12 elements, 3 this side, 4 that side. So in this box, when x is equal to 1, y is equal to 1, it is 2, x plus y is equal to 2. So I can write this probability of x is equal to 1, y is equal to 1, plus, when more it is possible to happen, when x is equal to 2 and y is equal to 0, here it is possible. So probability of x is equal to 2, y is equal to 0, that is why it is possible. And when x is equal to 3, y is equal to minus 1, then also it is possible. So see, out of the 12 boxes, the probability from those 3 boxes are added to get probability of z is equal to 2. So it will be P1 Q2 plus P2 Q1 plus P3 Q3. Yeah, that way I have given this to be the probability of 3. Okay, this is the Q3. Yeah. So that is the probability of z is equal to 2. If you ask what will be the scenario for z is equal to minus 1, so minus 1 will happen where? Only here. So this is where it will be only minus 1. So I am writing the z value. Okay, this is where it is minus 1. This is where it is 0. This is where it is 1. This is where it is 2. This is where it is 3. And this is where it is 4. Check. So does something click in your mind? Do you understand what pattern it is taking for this sum? And what is the general formula for obtaining the probability mass function for sum of 2 independent random variables? So we can split in the general scenario. You have already understood, but nevertheless I am writing it. So probability of z is equal to some small z for any value. It can take from here. that will be equal to probability of x plus y is equal to small z, that I can write as sum of, so sum of probability of x is equal to some value small x and y is equal to some value small z minus x. And now they are independent, so I can split them. So I can write them as probability of x is equal to x, probability of y is equal to z minus x. So these are the probability mass function of these two, and this runs for x is equal to for all x, all small x which are possible, all small x which are feasible. So here you can see that the small x is different for different values. So for -1 and 4 it can take only one value, for 0 and 3 it can take two values, and for 1 and 2 it can take three values. Okay, so this is equal to basically the PMF, the probability mass function, we can say Px, Pxx and Py z minus x. I can write in terms of the probability mass functions of the two random variables. These are the marginals. Okay. This is called the discrete convolution. So if you are taking digital signal processing, you will understand this. So over there it will be done. So this is the discrete convolution. We are quickly coming to continuous convolution as well. Convolution of the two functions P capital X and P capital Y, the probability, marginal probability mass functions of X and Y. Okay. If X and Y are continuous, I am taking liberty to quickly move towards the density function. So if I write the density function of z, xy are continuous and xy are independent, so z is equal to x plus y, that is also continuous, right? So fz of some small z, that will be equal to fz, this is the density function of x plus y is equal to z essentially. Yeah, this is the small z, say. Okay, so that I can write as, if I should actually do from probability, not from density function itself, it will be better to work for the probability. So probability of z, z is less than equal to small z. So this is what, this is essentially the distribution function. This will be equal to probability of, I should not write any subscript here, so this will be equal to x plus y is less than equal to small z. So that I can write as the joint scenario, that x is less than equal to some small x and y is less than equal to z minus x, isn't it? Now if they are independent, then these two probabilities are independent. Now this x, okay, sorry, this x can run over the real line, it can have any value as long as these two conditions are satisfied. So essentially this is equal to not this but the integral over the entire x axis. So I can write in terms of the differential probability, I should write, so which is basically that corresponding distribution function, and I am running over the real line corresponding to the x. So this will be equal to over the entire real line for x, I can write in terms of d of this, I can write as p x is less than equal to x and p y is less than equal to z minus x. Now here you can clearly see that these are basically the corresponding density function, distribution functions, marginal functions for x and y for z minus x. Now what is this? This is also a convolution. So this is also the corresponding convolution formula for distribution functions. So if these are continuous, then this can be written as, if you take derivative here, so that derivative will enter here, and these two derivatives will make them. So f z, the density function, which is the derivative of this, so it will become over the real fx x, fy z minus x dx. So which is essentially the convolution of fx and fy at z. So this is the like continuous time convolution, we can say, which you have already seen many times in signal systems and analog communication, even network theory. Now, when convolutions come, can Fourier transform be left behind? Of course not. So we know that Fourier transform will be a fantastic tool. So over which the Fourier transform will work? Over the density function, of course. So then like we get, we can manipulate many things in a better way, and which will lead to the understanding of what will happen when many independent random variables are added together. So which will lead to, say, central limit theorem. So to go there, I define the Fourier transform, which is called in probability literature, it is called the characteristic function. So it is defined as psi. I have written psi somewhere else as well when I talked about. Okay, let me write in terms of capital psi. That is fine. So capital psi of I omega is equal to expectation of e to the power I omega x. So that I can write as integration over the real e to the power I omega x dfx. In this way I can write. So for continuous random variable, if x is continuous, then this will be equal to, this characteristic function will be equal to integral e to the power I omega x fx dx. This is the density function. So that is what? That is essentially the Fourier transform of fx. Okay, fine. I have written plus here, but that does not matter, right? Whether you are traveling in the omega circle counterclockwise or clockwise, that is only a matter of convenience. In probability literature, historically, they have taken this to be the Fourier transform. Okay, so this is basically the Fourier transform of fx. So from this characteristic function, you can get the probability density function as well. So the density function can be recovered using the inverse Fourier transform. I am not taking any assumption anymore, because we know very well there's these are integrable, these are L-bar function. Fx is a positive function which is like integrable to 1. So this is definitely L1. So there is no issue with integrability and all. So inverse Fourier transform of course exists, and that is equal to e to the power minus I omega x d omega, isn't it? Now this Fourier transform form actually gives us some remarkable characteristics of this. That is why it is called characteristic function, because I can get all the moments if I know the characteristic function. So let me show how. So suppose this characteristic function is this one. So what I can do, I can take derivative of this characteristic function. Take it. So how to get all the moments? So take the derivative d psi I omega d omega. So that is equal to differential under the integral sign. So that will be equal to, here the issue is not that severe because these are function of x only. So it will be I x e to the power I omega x fx dx. Now so I you can take this side. So if you take this side, it will be minus I d psi I omega d omega, and now compute the value at omega is equal to 0. If you do that, then it will become x e to the power I omega x will become unity fx dx. What is that? That is expectation, isn't it? So expectation is equal to this. You can take more derivatives. So d2 psi I omega d omega will be equal to I square x square e to the power I omega x fx dx over the reals. So you can again see, so minus I whole square d2 psi I omega d omega, that will be equal to x square fx dx. So that is equal to e of x square. So you can generate any arbitrary moment. So arbitrary moment you can generate if you know the characteristic function. So this will be equal to minus I whole to the power n dn psi I omega d omega n, compute at omega is equal to 0. So that's the so-called DC, right, in that corresponding frequency. So this moment, this characteristic function, it will be useful soon when we talk about central limit theorem. But okay, so central limit theorem I will take some more time. We will, that will take some 15-20 minutes. I can complete that. No, fine. I'm leaving it now. But before leaving it, I want to mention one more thing, that is another useful idea which will be again required for communication, which is called the Hilbert space construction of a random variable. So Hilbert space of random variable. Now in random variable, one thing is interesting, that the mean, the expectation value, it talks less about how the distribution function is like mapped, or what is the kind of dispersion or different kind of like norms of the distribution function. It more or less, it talks about the so-called DC value. So it's like how much, like where exactly the distribution function or density function is placed on the real axis, on the real line. So suppose I am having two density functions, so two distribution functions. Suppose one distribution function is here and another distribution function is here. They are exactly same, only it is a shifted version. Okay, so if you compute the like second order central moment, which is the variance, these two distribution will give you the same variance. If I ask you that how, so if I ask you that what is the probability measure in the corresponding probability space, possibly they are same. Why? Because like the density function looks exactly same, distribution function looks same, means the corresponding derivative will also look same, but only it is only a shifted version. So the placement of the values are changed. So if I do the following transformation, suppose y is equal to x minus x plus c, suppose, where c is a constant, I can get this distribution function from this distribution function. Suppose this is fx and this is fy. So it is only a shift in a constant value or a DC value. So we can say this to be a DC shift or something like that. But inherently, in terms of the probability behavior, these two random variables are identical. So this is also a function of random variable, but here both the random variables are same. Only thing which is different is a constant. So we say that if two random variables x and y, if the difference between two random variables x and y is a constant, or the trivial random variable, I can say, a constant, then we say that these two random variables are identical for all probability purposes. So we don't distinguish between them. We say that they are almost same. They are same. for all practical purposes. That makes sense because this is a real line and the placement of 0. Suppose we are working on some values of voltage. So we are talking about some voltage output of some device and we are finding out a distribution. The voltage value is random. So we are talking about some distribution. So essentially this C is nothing but a DC. So you can block that DC, you can take down the entire thing around 0, nothing will change. So the voltage behavior characteristics will remain same. So that's why these two random variables are assumed to be equivalent. So they are assumed to be equivalent. With this understanding, what we can do without loss of any generality, we can assume that expectation of the corresponding random variable is 0. It does not change anything, isn't it? Because what I am doing essentially, so suppose there was some random variable x which had some expectation of ex. So this was the expectation, this is the real number which may be non-zero. What I am doing, I am taking a new random variable y is equal to x minus ex. So this is a constant, this is the so-called DC and you are doing a DC shift. So the new random variable which you are obtaining is basically the old random variable minus a constant. So these two random variables are equivalent. These x and y are equivalent, isn't it? But the good thing is that what is the expectation of y? Expectation of y is expectation of x minus expectation of x, that's the constant, is equal to 0. So I have brought down the random variable in such a way that its expectation of 0. So without loss of generality, we can say that whatever random variable we will assume, they are having 0 mean, their expectation is 0. Not only that, this gives us another good thing, that is the variance and the second moment, because central moment around 0 is essentially the second moment. Those things are same. So now variance of y is nothing but e of x square. So in this particular case, so without loss of generality, for any random variable, if you take that the mean is 0, the variance is itself, isn't it? Ex square is equal to ey square, I mean, ey square, So because expectation of y is equal to 0. Now, not only that, suppose now you have two random variables x and y, and if in the same understanding you assume that e of x is equal to 0 and e of y is equal to 0, both are DC shifted, then we know that their correlation is nothing but the covariance. They are same. Okay. The so-called Hilbert space of random variable, how it is constructed, how it was conceptualized, let me now tell about that, the last part. So what is the random variable? Let me tell you a nice joke about random variable, Hilbert space of random variable. So there is a saying by Voltaire, you know about the Holy Roman Empire, right? So Voltaire famously told, Holy Roman Empire basically between say 800 AD to 1800 AD, 1806 I guess to be precise, there is a group of nations in Central Europe. So these Germany, Romania, Czech Republic, Belgium, Northern Italy, Switzerland, etc., etc., even Western France. That area is called the Holy Roman Empire. So this joke was, Voltaire famously said that Holy Roman Empire is such entity which is neither holy nor Roman nor an empire, because there was no Pope involved in that empire anymore. There is no Rome in that empire. Rome is outside, and it was a conglomeration of several independent states, so it was not empire. Now we can state a similar joke about random variable. Random variable is something which is neither random nor variable, isn't it? Because the way we have constructed, like we have defined, you understand it. Random variable is nothing but a function, a map from the probability space to the real line. So this is the random variable. So is there anything random about this map, about this assignment? Not at all. It is well defined. It is very deterministic. The probability is there in the probability space. But the way the probability is induced, the induction, the function, the map, that is very much deterministic. It is unique, it is identical. Okay. So it is a deterministic function, deterministic map. It is neither random nor variable. Now, if it is a function, we know that a function can be thought of as a vector. When we developed functional space or signal space, you know that any function can be assumed to be a vector. It is nothing but you are taking values over real line, whether that is finite or countably infinite or uncountably infinite. That's a different story. It can be a finite function, it can be a discrete function, it can be a continuous function. But nevertheless, it is a function. And if this is a function, I can make a space out of that. So there can be multiple random variables from this probability space to the real line, and I can assume them as a vector in a particular space. So I construct a space of random variables, and this is a like generalized random variable in the sense that all the random variables are having expectation 0. So this space is constructed where all elements are having 0 mean. Zero mean, then only we can construct this. Then for any random variable, so the random variable is taking value as x. So if I ask you that for any function, so what is the L2 norm? Now normally when you compute L2 norm, you basically compute the energy, but here there is a catch. Here we are not computing the energy or the L2 norm only with the function, rather we are computing the integral in the Stieltjes format, where there is a like bias function, there is something which is basically the weight. So this energy function, this L2 norm which you are computing, this L2 norm is weighted. So we compute the L2 norm of the random variable as integral over the entire region x square dfx, I can say, or fx dx for continuous. Okay, so this common definition will work. Now what is this? This is essentially the variance, which is same as the variance sigma x square, I can say. So sigma x, this is the square of the norm. Yeah. So sigma x, the standard deviation, behaves like the distance. So this is the so-called distance function in this Hilbert space. And how to compute the inner product? So inner product between 2x and y, in the same way, it is xy, but now you are doing weighted, because this is like having a distribution function, and I am computing it for the joint distribution of x and y. So what is this? This is nothing but the correlation or covariance. The same. So this is the correlation of x and y. So you remember from school days that what is a correlation coefficient? Correlation coefficient is what? It is basically the correlation between x and y, covariance divided by the corresponding standard deviation, isn't it? So I can write it as the inner product divided by the norms x and y. Do you remember anything? This is essentially the angle between the two random variables, two vectors. So this is the cos theta, if I can say that theta is the angle between the two vectors, between x and y. And you know this correlation coefficient, which it was written as R, right? Rxy. We know that Rxy always takes value between +1 and -1. So that fits with the cos theta thing, right? So if you are given two random variables, you can immediately compute the cos theta between them by this formula. This is the construction of a Hilbert space of random variable, which are having this this special form, which are having all zero mean. This is accepted. Okay. So with this I stop here now. In the next class I will talk about the central limit theorem, and then I will move towards the random process. So that is where our journey will start. So we are having good progress till now. Random process, I will try to finish the topics which I want to finish in say 2-3 classes at most. Okay. So till then, bye.